Hello, and welcome to another module of the Design Patterns training. My name is Martin Schroeder at SwedishEmbedded.com. And in this module, we're going to talk about the object pattern. If you don't want to wait until I release another module of this course next month, then you can get all of the content for this course, including all of the design patterns right now in one of three forms. So you can get the book on Amazon, you can get the Udemy course, or you can get a subscription on my website, which also includes a live Q&A with me. So if you go to Amazon, you can search for the book title, Embedded C Programming Design Patterns. Here is the book. If you go to Udemy, there is a course with the corresponding name, Embedded C Programming Design Patterns by me. And you can also find the book content as PDF files attached to every section. And if you go to the website, you will have also the book content and the video content and also the Q&A. So when you're registered, you click Join Now here, you fill out your details, you pick the student account, click Continue. And then once you're logged in, you're going to have a link here where you can join the Zoom call. So it's 5 days and 3 hours until the next Q&A when I'm recording this. And the Q&A is every Wednesday at 19:00. So let's jump right into it and talk about the object pattern. The object pattern is the most important pattern in C programming because it allows us to separate our modules into objects, and it helps us to avoid having global variables in our code. So the object pattern is at the bottom of all other patterns. Many other patterns we're going to be discussing in this training are going to be building on top of the object pattern and adding additional features to it. But at the core, we talk about objects. And you probably heard about object-oriented design before, but in C programming, we have to think about it slightly differently. So let's jump right into it and look at the object pattern. First of all, let's look at the defining characteristics of the object pattern. The most common and the most obvious characteristic of the object pattern is that we always have the self pointer. And this is going to be a parameter that we pass to our functions that operate on the structure that contains our data. So instead of having global variables, instead of having a disorganized global namespace with lots of different types of data, we try to group our data into structures. And when we have functions that operate on those structures, we pass the self pointer. So data that our functions operate on is never accessed globally. Instead, it is passed as a parameter to our functions, which makes it very clear to the programmer and to whoever is looking at the code where this data comes from, but also who is allowed to modify the data. So when we have it as structures, we can easily say that the only functions that are allowed to modify that data are the functions that are designed to operate on that data, and no other functions. So you kind of implicitly avoid this global modifications to your data that can happen at any time in a conventional C program by grouping things into objects. And another third defining characteristic is that we don't use static data, especially in functions. So we don't place variables in functions that are declared static, which means that they're basically global variables, but they're just placed inside a function scope. We don't do that. So we place all of our variables in the context, which is pointed to by the self pointer, and we access that data through the self pointer instead. And this has a fascinating side effect that is very, very useful for the code organization, which is that the data flows along the call graph. What do we mean by that? So basically, when we pass the self pointer to our functions, the data is flowing along the call graph to whatever function it is that you're calling, and you can interpret that as borrowing this data to that function for a short period of time. And then when the function is done with that and the function returns, then you pass that self pointer to another function, which operates and maybe does something else with that data. But the clear distinction here is that the data is flowing along the call graph, which means that it's very easy to add synchronization to this data access, because it's very clear that you're actually accessing data that is part of your context, part of your self pointer. So if you want to add a lock, for example, you could just easily add it to the structure that is pointed to by the self pointer, and that makes it clear that whenever you try to access that data, you need to use locking to ensure that you have concurrency safe code. The opposite of this is when you have data that is outside of the call graph. So for example, static variables, they're outside of the call graph. Global variables are also outside of the call graph. And that introduces side effects. So you can have other code change that data. And then every time you call your function, you get different result because the data that it's using is different. But when you have the data, when all of the context is passed through the self pointer, you always get the same result. So if you pass the same data to the function, you get the same result because there's no outside dependencies. All of the data is kind of provided to the function, and it's very clear that, well, this function operates on this object, and so there cannot be any other side effects. So testing is easier as well. What are some of the use cases then of the object pattern? And if we were to generalize the object pattern, we would say that the object pattern is useful in all cases. Like every time you start coding something in C, you should use the object pattern by default. But I still decided to create a list of common use cases just to give you something concrete. So the most basic use case is that you're trying to group data. So you're trying to group related variables into a structure, and you're trying to then create methods that operate on that structure. So this makes things very clear. Instead of having a whole bunch of global variables that are not related to each other, you now have your structure, which only contains the variables that are relevant for that object. And when you group data that way, you can also instantiate all of that data at once. So you can just instantiate instances of that structure, and it becomes very clear that you can have multiple instances of the same object. You cannot have that if you use global variables, for example. Singletons. So when you implement singletons, it's also a good idea to group data. Like even though you have only one instance, when you group the data together, now you make it very clear that when you access something that is part of the self pointer, it's part of the context that is shared. When you access something, just a variable directly, it should always be a local variable. It should never be a global variable. So it becomes very clear when you're looking at the code, what the code is actually doing. So you improve clarity. So even if you're using singletons, in the singleton implementation, you would typically just group the data into a structure, and then you would have just one instance of that structure. Abstract interfaces. It's very difficult to implement abstract interfaces in a reliable and clear way unless you start with the object pattern. So we're going to look at abstract interfaces farther down this training, and we're going to use the object pattern to make sure that we can have virtual methods added to our object instances. And we can then easily differentiate between different instances of the same type, and we can have different when we call our virtual methods, we would be operating on different instances. So it becomes very, very easy to implement higher level concepts when you start with the object pattern at the bottom. The next use case is multi-threaded design. So when you group data in this way, and when you make sure that you pass the data along the call graph, multi-threaded design becomes just very easy. It becomes very simple to tell what data you should be locking and what data is okay maybe not to lock. Because obviously the data that you wouldn't be locking, the data that you're not accessing through the self pointer, that's going to be local data that is just declared in the scope of the function, basically stack variables. So there's no need to lock them because you're instantiating them for every call of the function. So multi-threaded design becomes very, very simplified, and it's much easier to write bug-free code when all of your code is structured into objects. And the last use case that I want to mention here is opaque handles. So we're going to look at a special design pattern in the next module, where we will look how we can actually hide the definition of the object. But when we want to access an object that we don't have the definition for, we typically pass pointers. And those pointers, when you use the object pattern underneath, you would be passing basically pointers to structures that you don't know the full size of the structure, but you just know the type of the pointer. And so you can have opaque handles that represent instances of the same type, but you can now just pass them to the same functions, essentially, that take the self pointer, and now these functions will be operating on data that is private to the module, that is not visible to you as the caller, but you can still use the same interface. So it's a very flexible pattern, and it's It's the first thing that you should be doing when you start refactoring older code, just to kind of clean up the code and make sure that the code is separated enough so that you can do further refactoring later. But the first step is usually to start separating the objects, to start identifying what parts of the code belong to which particular object. Now let's look at the implementation of the object pattern. So in reality, it's just very, very simple. So basically, what you do is you have your declaration file, which is the header file in C usually. And in your header file, alongside of your API, you also declare the object. So the object in C is basically a structure. So C uses data structures. And when we group variables into a data structure, we call it an object. But the main difference is that all of the functions that operate on this type struct myObject, all of these functions take the self pointer as the first parameter. And it's a very good idea to keep the self pointer, like to use the same name everywhere. So I use self because this corresponds to how Python is written in C. When you have the Python interpreter, it usually uses the self as a designator to the object you're operating on. In C++, you would have this, but I wouldn't use this in C because then you cannot compile your C code with a C++ compiler because it's a reserved keyword, this. So I use self, and I think that it's the one that is most generic and very easy to follow. So I would really recommend that you use the same name everywhere, because it makes it clear to whoever is looking at your code that when you're accessing some data, you would always prefix it with self. And that makes it very clear that this data is something that has been passed to the function as a context that is normally outside of the function, but now you're operating on that particular context. And then you have your C file, which is the definition. It's going to contain the definitions of your functions. And for all of your functions, you would take this self pointer, and even for the init and the-init. So these are basically corresponding to the constructors and destructors in C++. And even if you're coding in C, you should have a standard way of constructing objects. So I use init and de-init as a standard naming convention for constructor and destructor. And in the constructor, it's important that you clear the memory. This is one of the most common mistakes in C, that you start using a data structure and you haven't actually initialized it. You haven't initialized all the fields in it. So just to make sure that you never forget to initialize some field. So for example, if you're placing a data structure on the stack, if you haven't initialized it, it will have garbage in the data. So to avoid that, I always clear all of the fields of a data structure when initializing it. And then after this line, I can obviously initialize some of the parameters to whatever they should be. For the prefix of all the functions, I use the same name as the type. So one of the very nice conventions to use is to name your type exactly the same way as the file where you place your type. So here we have the struct myObject, and we place it into myObject.h. And for namespaces, to emulate namespaces in C, you would basically place your files into different directories. So when you want to, let's say you have a system namespace, so you would have a directory called system, and then in that directory you would have myObject. So whenever you include system myObject.h, it's kind of like you were organizing things in C++ using namespaces. But obviously C doesn't have namespaces. So in C, we have to create those conventions just to make sure that we structure our code correctly. But even if you code in C++, having a set of conventions to use, like for example, that you always define a constructor, is a very good practice, because you make things predictable and you make the expectations clear as well. And when it comes time to use this object, you include the file for the type that you want to include into your application. And then you instantiate an instance of this type. So in this case, we have a structure for the application, and we have our type here. And we then initialize, we call init on this type like this. Some of the basic rules to keep in mind, and this is just to help you when you're writing your code, is that all of your functions that are kind of considered member functions of this type, all of these functions, they're thought to act on that instance of the object that you're passing into the function. So if you look at some older C code, you will see that there are a lot of functions that just use global data. And it's not clear what data is this function acting on. So when you apply the object pattern, it becomes very clear that you're passing this instance, and that is the instance that is referred to as the self. That is the instance you're actually operating on. You're acting on that instance. And functions prefixed with the object name. This also makes it very clear that this function is operating on a particular instance of a type. Another big side effect of using the object pattern in the way that I just described is that you're making your functions reentrant. And reentrancy basically means that you can call the function from different threads, and you will always get the same result provided that you pass exactly the same data. So you can have the function can be entered from multiple threads safely. That's basically what reentrancy means. And if you look up reentrancy in general, you will see that there are 3 rules that a function must adhere to in order to maintain reentrancy. And the first rule is that there is no global static data access. So you cannot access global variables. The moment you start accessing global variables, you're no longer reentrant, because now you can have the same call from 2 different threads, and it will return different result because the data has changed outside of that function. Number 2 is that there is no self-modifiable code, which is kind of obvious. We almost never have code that modifies itself. But this is still a rule that needs to be true in order for a function to be reentrant. And your function shouldn't be calling any other functions that are not reentrant. So one of the biggest reasons to apply the object pattern is that you're trying to make sure that your whole software stack is as reentrant as possible, because that helps you then to create code that is thread safe. So if you're if you have a mutex or other way of controlling access to some data, you can be sure that that data is not going to be changed from outside by some other function that maybe is not using the same access control. So you can, for example, if you have global data, you can obviously add a mutex in one place, but then if there is some other code somewhere else that modifies that data, then that code also needs to use the mutex. And because the data is global, you can never fully guarantee that that data is not modified anywhere else. It could be modified inadvertently. Like you can have, maybe you're making some change to one portion of the software, and you're thinking that you're making it thread safe, but then the data is still global, so there's no way of guaranteeing that. So when we have when we use the object pattern, we always have to keep track of this context, and that in turn helps us to guarantee that we can easily search for places where this context is being used, for other places where it's used. So it becomes very easy to find those places as well. So it's always a good idea to maintain reentrancy. And to keep this in mind when you're writing code, because those, especially the first rule, is going to help you a lot to write clean and maintainable code. So let's have a look at some of the benefits of using the object pattern and applying it everywhere we can apply it. We get a clear scope. We know that the scope of this self variable is a borrowing scope. We're basically borrowing that variable for a while, we're doing something with it, and then when our function returns, then that data is safe to pass somewhere else. We get reentrancy, provided that we follow the rules on the previous slide. We get ease of locking, so it becomes very easy to add thread safety to our code if it is needed at a later point in time. We simplify our testing because we don't have any data that is outside of our file that our file relates or depends on. So we can easily instantiate our objects in the test code, and then we can test our functions with dummy data, and we can modify those objects as we need. But we don't need to instantiate each and every variable, each and every global variable manually in the test code. We can just instantiate the whole structure, and it's just very simple and easy. and we get a clear data flow. So we know how our data is moving through the application when we group our data into objects. So what are the drawbacks of the object pattern? Well, if we look at the object pattern without any additional features, just the object pattern itself, then it doesn't provide us with a way of hiding our implementation of the data structure. So we need to have the data structure exposed in the public header file of our implementation in order for the caller to be able to instantiate it, to know its size and everything else. So our header file by definition needs to include the type definitions for all of the types that are being used or put into this data structure. And the second drawback is that if everything is an object, you can run into situations where you can sometimes have higher memory consumption than necessary because you're duplicating some features across all of the instances of the object. And there's usually ways to deal with that. Like you can have a local singleton in your C file implementation that contains only the things that are shared among objects. For example, an example could be, for example, let's say you have a data buffer that is shared among all connections just to save memory, because maybe you have too little memory on your microcontroller and you cannot have like a separate buffer in every connection object. You would then place that buffer outside of the connection object. So there is ways to deal with that, but this is something to keep in mind also, that because you can instantiate multiple instances of the same thing, if there is something in one instance or in the definition of the type itself that takes a lot of memory, then the memory consumption is going to be the sum total of all the instances that you're instantiating. Best practices of the object pattern: avoid all the static data. Never have any static data in your functions. Always use the self pointer. Use consistent naming, and standardize your init, deinit functions so that it's always the same, so that there's always a requirement to call the init function when you're instantiating the type. So that's it for this. You can read through this slide, pause the video, and just basically this is a recap of what I've already said, but it's still good to keep this in mind. And the pitfalls. So the biggest pitfall is obviously not following this pattern, because you end up with things like this. So this is very common in C code. You will see things like this. So this is a function, and this function is using some global data that is not apparent to the caller. So the caller just passes a parameter to this function. And also what you will see that a lot of C code doesn't even follow any naming convention. So you would have just arbitrary name. Maybe there is no my object here at all. There's just do something. And when you see this kind of call, do something, and then there's a parameter, it's not clear at all, like what object is this function operating on? And this is the things that you want to fix. So this is the kind of code you want to fix with the object pattern, so that it always takes a context. And this makes it very clear that this function operates on an instance of my object, and the instance pointer is here, and whatever modifications that are done to this instance pointer, they're going to end up inside this instance pointer after the function returns. So avoid this kind of stuff. And the second pitfall is obviously using external variables. So whenever you see something like this, this is very, very bad design. So if you look at this code here, for example, you have your C file, and it's modifying a global variable that is actually instantiated somewhere else. So this code is not reentrant. And by the way, this code is not reentrant either, but it's better than using an external variable. But this is really, really bad code. So if you see any code like this, make sure that you definitely just remove this extern, move this to an object, and then restructure any code that uses this so that the data flow is clear, so that you have an instance pointer somehow ending up inside this code, and then so that the data flow becomes very well defined. alternatives to the object pattern. The primary alternative is the opaque pattern, where you're creating things on the heap, and you're just sharing a handle, which is basically just a pointer to the caller, and then the caller basically just uses that in the same way as an actual instance, but now you're passing a pointer to all of the member functions, which then represents your instance. And the singleton pattern, that's another alternative to the object pattern, where you have only one instance. So as long as you're following the patterns, and as long as you're doing it consciously, when you decide to use a singleton, as long as it's not something that just automatically happens, it's probably a good choice. But if you end up with a source code where everything is basically a singleton and everything is just a bunch of global data, that's when you have a problem. That's when you will find that it becomes exponentially more time consuming to maintain that kind of code. So when in doubt, always use the object pattern. This is the most versatile pattern, and if you're not sure at all what pattern you should be using for your code, then just go with the object pattern. It's always a safe choice. And it's also the fastest way of cleaning up code, because the moment you start adding those instance pointers, it becomes very clear what code depends on what other code. And a lot of these dependencies, they will just float to the surface, and then you can start refactoring them and fixing them. So the object pattern is there to help you with the code organization. When you start applying it, it by definition kind of makes your code, it kind of forces you into organizing your code properly. So keep that in mind and start applying it. Let's check your understanding of this pattern. So why is it so important to avoid static variables inside functions in C, especially if the function is an object method? Why should you avoid them? What does it have to do with reentrancy? That's a tip I'm going to give you. Number 2, why do we avoid functions without parameters? What negative properties do these functions have when, and why is it a bad design flow to use that kind of function in C code? Why do we call our pointers to context as self? Why don't we call it me or object or device? Why do we use self? What is the main benefit of using self as a standard pointer to the object that we are operating on? Why is it sometimes necessary to instantiate objects locally in the C file, for example, as singletons? What does that have to do with memory consumption, for example? And what is the intent behind that? So when you instantiate some portion of your object inside your C file, what effect does that have? So you're taking some functionality, something that is shared between different instances, and you create just one instance of that functionality and one instance of that data. Why is it sometimes necessary to only expose a pointer to the data structure outside of the actual implementation of the code? What benefit does that have? Do you need to know the information about all the types that are part of that data object, or can you just know the type of the pointer to that data object if you hide that inside the implementation? Why is it a good practice to always name the header file and the C file with the same name as your data structure? And lastly, why should you never use extern when you're referring to your data? What does extern, what is the biggest problem with using extern? How can you guarantee that that data is not modified while you're running your function by just some random code somewhere else? So that's it for this module. I'll see you in the next module. Next module is going to be about the opaque pattern, and we're going to look at how we can hide our definition of the object in the implementation. That's it for now. See you later.